Hello MFSL, this is Mr. Payton. We're about to do a video mini lesson of trig identities for your Regents Prep. Remember, Tuesdays are reserved for mini quizzes on the previous week's Regents Prep, and then a mini lesson that will be setting up the next week's investment activities, the opening activities in which we're engaging in Regents Prep problems. It's important that we keep these mini lessons to Tuesdays so that we can see all the important and exciting content, new content that we have planned for this fall. And all that new content will also be on the Regents, so it's really important that we stick to this. To that end, I hope that moving forward we'll try to figure out how to manage our time better so that we complete these mini lessons within the class period on Tuesday. For this one, we obviously did not complete it, so as promised, we're doing a video. So thank you for having your blue folder out. Thank you for referring to your pink reference sheet as we go through this lesson. And thank you for making sure you have everything down on your sheet that, again, will be inserted into the middle section of that folder. So without further ado, what I have projected here is where we left off. We are showing that secant squared of x minus 1 over secant squared of x is equivalent to sine squared x. That is our goal. So we want to get from here to here. In order to get there, so far we noticed that secant squared x minus 1, that reminds us of Pythagorean identity. There's a squared, there's also a 1, so we thought Pythagorean identity, and lo and behold, one of our versions of the Pythagorean identity was that tan squared of x plus 1 is equal to secant squared of x. We manipulated that to show that secant squared of x minus 1 is actually equivalent to tangent squared of x. Okay? Secant squared of x minus 1 is actually equivalent to tan squared of x, so that's what we've done so far. We substituted those in. Next up, remember this hint down here. General rule of thumb is when simplifying, it's advantageous to us to express things in terms of sine and cosine so we can see what cancels out and get it to its simplest form. So to that end, we're starting to think, well, tangent squared of x, secant squared of x, we got rid of that minus 1 that was in the way. Now, let's see if we can express these in terms of sine and cosine. So far, we talked about how tangent squared of x is equal to sine squared of x over cosine squared of x. We also know that secant squared of x, applying your ratio identities, would be equivalent to the reciprocal of cosine squared of x, 1 over cosine squared of x. So let's plug these in. We know tangent squared of x, again, is equal to sine squared of x over cosine squared of x. So I'm going to plug that in as my numerator, just highlighting to make sure you're with me. All I did was said that is equivalent to that. Next, we know that secant squared of x is equivalent to 1 over cosine squared of x. So highlighting this to make sure you're with me, this denominator is equivalent to 1 over cosine squared of x. That's just applying the ratio identity. Secant is the reciprocal of cosine. S goes with C, C goes with S. Continuing on. Remember, dividing by a fraction is the same thing as multiplying by the reciprocal of what you are dividing by. So, whoops, don't write that down. The reciprocal of 1 over cosine squared of x would be cosine squared of x over 1. At this point, you should notice something very convenient happens. The cosine squared of x is canceled, which leaves us with sine squared of x over 1, which of course is sine squared of x. We have indeed proven that secant squared of x minus 1 over secant squared of x is equivalent to sine squared of x. We met our goal. Great, congratulations, let's move on. So please flip to the back of that page and take a look at example 2. Note that for example 2, 3, and 4, you should now be looking at your A2 trig, Regents reference sheet, the bright pink one that should be prominently displayed in your blue folder. So in this problem, it says if cosine of an angle, call it theta, is equal to 4/5. then what is cosine of 2 times that angle? Or in other words, double that angle. Oh, double that angle. Look at your pink sheet. We have what are called functions of the double angle. Those are going to be handy in this case, because this is doubling the angle. 2 times the angle, 2 times theta. So notice, when you look at the functions of the double angle for cosine, there's actually 3 different versions. So I'm going to ask myself, which version should I use in this case? And to help me figure out which one is most useful in this particular situation, I'm going to think about what information I actually know. And the information I know is the value of cosine of the angle. Note that given that information, we could solve for sine of that angle, but that would be extra work, because there's a version of the cosine double angle identity that involves simply using just simply uses just the cosine. And that version is cosine of 2 times theta is equal to 2 cosine squared theta. Notice I'm calling it theta instead of a. On your reference sheet it is called a. Here we're calling that unknown theta. It's fine, just a variable. So 2 cosine squared theta minus 1. Now, before we proceed any further, I just want to remind you that this notation, cosine squared of theta, is equivalent to cosine of theta, whatever that value is, squared. Okay? This is just an easier way to write what's on the right-hand side. So, we have, plugging in what we know 2 times whatever cosine of theta is. What is cosine of theta? Cosine of theta is 4/5. So we're going to plug in 4/5 as our cosine of the angle. Notice it is not cosine of 4/5, because theta is not equal to 4/5. Cosine of theta is equal to 4/5. So that's cosine of the angle. I plugged that in, and that's being squared. Minus 1. At this point, it's pretty straightforward. You guys should be able to do this just fine. 4/5 squared is 16/25. Minus 1. 2 times 16/25 is 32/25. Minus 25/25 is 7/25. Check my work, but I think that's right. All right. Moving on to example 3. In example 3, it says, what is the exact area? Exact area of a parallelogram that has sides measuring 10 centimeters and 14 centimeters and includes an angle of 120 degrees. Note, it says exact area. That's making me think, since we're going to be dealing with trig, that's making me think of those special unit circle angles that we're familiar with. For example, 30, 45, 60, 90, 120, so on and so forth. Or in radians, pi over 6, pi over 4, pi over 3, pi over 2, so on and so forth. And notice, indeed, the angle we're going to be working with is one of those special angles. So we'll be able to determine the exact value. We won't have to plug something into our calculator and get a decimal in this particular example. I'm going to start by drawing a picture. This is always a good approach for anything that involves anything with geometry related. It's good to have a diagram. So I'm drawing a parallelogram. It's not the most beautiful parallelogram, but recall that in a parallelogram, opposite sides are parallel, opposite sides are congruent, and the sides measure 10. I'm going to say that one's 10 because it's shorter, and 14. That means this would be 14, this would be 10 as well. Not super important, but just a reminder, opposite sides are congruent. And between the 10 and the 14, it includes an angle. So between a 10 and a 14, it includes an angle of 120 degrees. So that is 120 degrees. And I want the area of the entire parallelogram. Look at your pink Regents reference sheet. Do we have a formula for area of a parallelogram? Hopefully you said no. We do, however, have a formula for area of a triangle. How can we make this into a triangle? Of course. We can divide this into 2 congruent triangles by just drawing in a diagonal. I'm drawing the diagonal that way so that the 120 degrees can be the included angle between the two sides of the triangle that we know, 10 and 14. So we'll just be able to apply the formula. The formula for area of triangle is K is equal to 1/2 AB, which are going to represent the two sides we know, times sine of C. And the important thing to remember is this angle is the one included, has to be the one included between the two sides. And is that what we have in this case? It is indeed. Okay, the 120 degrees is indeed included, meaning kind of wedged between, is included between those two sides. So we can apply the formula. We're going to get K, which is representing the area of triangles, equal to 1/2 times 10 times 14 times sine of the angle, which is 120 degrees. This is going to end up being 1/2, or let's just multiply it out, sorry. 1/2 times 10 times 14, that's 7 times 14. 7 times 14 is, what's that going to be? 70 plus 28. Sorry, I'm blanking for a second. Oh, why am I saying 7 times 14? Excuse me, 5 times 14. 1/2 times 10 is 5. 5 times 14, I'm sorry that I misspoke, is 70. So that's going to be 70 times the sine of 120. The sine of 120, thinking of your unit circle, 120 degrees is in quadrant 2. The sine is going to be positive in quadrant 2 because sine is your y. That sine value is radical 3 over 2. Positive radical 3 over 2. This ends up being 70 divided by 2 is 35. 35 radical 3. But that is simply the area of the triangle we were working with. The triangle we were working with. So in order to find the area of parallelogram, I'm going to multiply this by 2 to get the total area. The total area is going to be 70 root 3. I'm going to call it square units because we're not given a particular unit, but it's square units because it is area. One last example. The triangle has sides that measures 22, 25, and 30. Find to the nearest degree the measure of the smallest angle in this triangle. You move a little bit quicker because I can only do 15-minute videos. I have 2 minutes to do this. So stay with me. You can always rewatch if it's too fast. So, 22, 25, 30. The smallest angle in the triangle is always across from the smallest side. So this would be our smallest angle. Okay? In order to find the measure of that angle, I'm going to ask myself which identity involves 3 sides of one angle, and that is the law of cosines. The law of cosines is, as it's written on your formula sheet, a squared is equal to b squared plus c squared minus 2bc cosine of a. The important thing to remember about this formula, really the only thing you have to remember, is that this angle is across from this side, whereas B and C would just represent the other two sides. Okay, so you might have seen some things just appear on the screen all of a sudden, and I apologize about that. I'm going to erase part of it. So what I've done is actually labeled this angle big A and this side across from it little a. Really, again, the important thing to remember is that this angle is across from this side, and then the B and the C are just representing the other two sides. So plugging all this in, it looks like this, as you see on the screen. Basically, we need to solve for A, so we're going to isolate cosine of A first. So isolate cosine of A, and then you're going to have to use inverse cosine to solve. So what you end up getting is 22 times 22 is 484 is equal to 25 squared is 625 plus 30 squared is 900 minus, let's multiply all this. 2 times 25 is 50. 50 times 30 is 150 cosine of A. I only have 15 seconds to do this, so let's just try to do this real quick. 45 minus 625 minus 900 this is negative 1041, is equal to